We started our new unit yesterday on electromagnetic radiation. You guys remember what causes electromagnetic radiation? I mean, there's 7 different types of EMR, right? And each of them are produced by a unique method. But in the end, one general category causes all types of electromagnetic radiation. John, what is it?
Movement of electrons.
Jesse, sorry. Sorry, Jesse, what is it?
I said like movement.
Okay, let's hold on for a second. You're not quite right, but you're on the right track here. If we have a stationary electron generates a gravitational field. It'll produce an electric field. It will not produce a magnetic field. If we have a moving electron or other charge, it will produce a gravitational field. It'll produce an electric field, and it'll produce a magnetic field. But those electric fields and magnetic fields are going to be constant in nature. If we have an accelerating charged particle, then we produce a gravitational field, an electric field, and a magnetic field, but those electric fields and magnetic fields are changing in nature. And that's important here. We got to have not just a constant electric and a constant magnetic field, but rather we have to have a changing electric and a changing magnetic field. Why? Why do we have to have a changing electric and magnetic field? Well, if I identify this as electric field number 1 and this as magnetic field number 1, in order to get electromagnetic radiation, electric field number 1 has to produce magnetic field number 2. And magnetic field number 1 has to produce electric field number 2. And then magnetic field number 2 produces electric field number 3, and electric field number 2 produces magnetic field number 3, and so on and so on and so on. A constant electric and magnetic field will not produce another magnetic and electric field, but a changing electric field will produce a changing magnetic field, and a changing magnetic field will produce a changing electric field. That's what EMR is the movement of energy from this spot that was generating the EMR to over here somewhere, right? And you can't get it moving from this spot that produced it to over here somewhere if you don't have a changing electric and magnetic field. So moving charged particles, Jesse, you said it's the moving charged particle that generates it. You're not that far off because they will produce an electric and a magnetic field in addition to gravity, but it's constant. And that doesn't cause the new field here and the new field here causing it to move over here. So you're almost there, but it can't be just a moving charge. It's got to be an accelerating charge. Does that make sense? All right. Now understand, though, that when E2 and B2 were produced by B1 and E1, understand that once those are made, these guys are gone now, right? These fields are gone. The energy has moved from position 1 to position 2. And then when B2 produces E3, when E3 produces B3, then these guys are going to be gone. There's another wave that replaces these waves. Sometimes you can get a continuous wave. This would be just a pulse. Sometimes you can get a continuous wave, but if you do get something to come in and replace E1 and B1, then it has to be caused by the charged particle continuing to accelerate. So let's say the charged particle slows down really quickly. It's going to produce this pulse right here, E1 and B1, which is going to produce E2 and B2. But as it does that, the energy gets transferred to E1, E2, and B2. But if you have the particle accelerating like this, constantly accelerating, then even though you have the energy from the first field going into the second field, you now have more energy put into it from this accelerating charge. So you got another E1 and another B1 rushing in to take the place of the one that just transferred its energy over here. Which way do they travel? This way, perpendicular. There's 3 words here that I would suggest are really important words. Okay, and they can kind of guide you to all of this stuff that we've just talked about. The first word would be accelerating. You got to have a charged particle, and that charged particle must be accelerating. If it's not accelerating, you don't get EMR. Why not? Because if you don't have an accelerating charge, then you don't have a changing electric and magnetic field. Changing is a pretty weak word here too, because if you don't have a changing electric and magnetic field, you don't have any kind of propagation of EMR. You just got an electric field and a magnetic field, and that's not EMR. If you don't have a changing field, then you don't have propagation or movement of EMR. Propagation at a right angle or perpendicular to both fields. So both fields are perpendicular to each other and also perpendicular to the way the wave travels. If one wave is on x-axis, one wave is on y-axis, the wave is going to travel on the z-axis, either positive z-axis or negative z-axis. If one is on the z, okay, one is on the y-axis, then it's going to travel either on the positive or negative x-axis. So accelerating, charged particles that are accelerating generate EMR. They got to be accelerating because accelerating particles produce changing electric and magnetic fields. Constant electric and magnetic fields don't cut it. They got to be changing in order to get this propagation of the wave. Propagation, perpendicular propagation of the wave. The wave travels perpendicular to both the electric field and the magnetic field wave. All right? You get those three words, and you're probably going to be okay with this. Even if it's hard to visualize for you, you're probably going to end up being okay if you remember those three words and kind of the context around those three words. All right? What else did we do yesterday? The types of EMR, right? Comes from the song. We will later on. Good. Oh, you're welcome. What type of EMR do we have first in terms of lowest frequency? Radio waves. Then what comes next? Microwaves. Then what comes next? Then visible light, ultraviolet. Good. So we got our 7 types of EMR ranked in terms of increasing frequency, also ranked in terms of increasing energy. As you go from left to right, frequency goes up, energy goes up, but also ranked in terms of decreasing wavelength. Frequency goes up, energy goes up as you go from left to right. Wavelength goes down as you go from left to right. You're going to have to rank these. You are. There's no question about it. You may be asked to rank them in terms of increasing frequency. You may be asked to rank them in terms of increasing wavelength, maybe decreasing energy. And what I would suggest you do whenever you get that question, whenever it is write down these types of EMR in terms of increasing frequency. And then if you have to rank them in terms of decreasing frequency or increasing wavelength, just read backwards. Gamma rays, X-rays, ultraviolet. It's easier to remember them in this order and then read them backwards if you need to after you've written them out than it is to memorize them forward and backwards. Got it? All right. You will have to rank them. There is also a possibility, albeit a far smaller possibility, that you'll have to identify what kind of EMR you have based on the frequency of that particular photon of EMR. Let's say you're given a photon of EMR that has a frequency of 10 to the 15 hertz. What is it? Let's say you have one that's 5 times 10 to the 14 hertz. What is it? Well, we got to be able to identify 7 different ranges of frequencies and wavelengths and energies for that matter. But the good news is, as I said yesterday, there's only 3 that you really have to memorize. Microwaves have a frequency range of 10 to the 9 to 10 to the 12. Visible light has a frequency range of 4 times 10 to the 14 to 7.5 times 10 to the 14. So what would 10 to the 15 be? That should be a 20. So it should be 10 to the 15 is ultraviolet. And what would this one be? Visible light. Okay, if it fits within one of the ranges you've learned, then it's going to be that type. If it doesn't fit within, then figure it out. 10 to the 15 doesn't fit within visible light or X-rays, therefore it's got to be ultraviolet. Let's talk about how each of these types of Sorry, one more thing. If you got a wavelength, you got to also be able to figure out what kind of EMR it is. But there's no memorization to do there. All you're going to do is take your wavelength, let's say 3 times 10 to the negative 8. Let's convert that to a frequency. F is equal to V over lambda. V is 3 times 10 to the 8. And it's 3 times 10 to the, V is 3 times 10 to the positive 8. And then lambda is 3 times 10 to the negative 8. That's going to give me 1 times 10 to the 16 hertz. What do we have now? Ultraviolet. Based on its frequency, right? We didn't know what it was based on its wavelength, but we know what it is based on its frequency. So let's just find the frequency and then do our thing. We can do the same thing with energy, except it's a different equation that you haven't learned yet. Ethan? V equals F lambda? Yes. Yeah. You also have the one for energy, but it's not going to make sense to you yet, so I'm not going to tell you what it is yet. All right. One more thing. We have to be able to identify as well the specific mechanism that produces each of these types of EMR. You guys remember what radio waves and microwaves are? Yeah, electric charge that's going. Electric charge that's going back and forth, back and forth. What about infrared, visible light, and ultraviolet? This is that situation where you're sitting in the upper deck of the Saturdome and you want to, oh, you see a vacancy, right? So you go back down to the lower deck. Yeah, electrons are transitioning from high levels to low levels, and as they do that, they give off energy in the form of a photon, infrared, visible light, or ultraviolet. We're going to say electron transitions in the atom. Different transitions produce slightly different frequencies of EMR. X-rays. Remember the dentist? Rapidly decelerating electrons? Get electrons going like unbelievably fast, 10 to the 6, 10 to the 7 meters per second. They crash into a target, they stop almost instantly. The energy that they had was in the form of kinetic energy. And that kinetic energy is now transformed into this photon energy, this gamma ray energy. And finally, X-ray energy, I should say. Finally, gamma rays are produced by nuclear decay. You got an alpha decay, radioactive decay, alpha decay, beta decay, nuclear fission. In all of those cases, we have matter is converted to energy. Einstein said that energy and mass are two different forms of the same thing, like ice and steam are two different forms of the same thing. We can convert all of our ice to steam if we want. We haven't really gotten rid of anything though, right? We still have the same amount of water, H2O. We can convert energy to mass and mass to energy. We still have the same total amount of energy / mass. In nuclear decay, it's like we're converting steam to ice. We're changing matter to energy. Matter is converted to energy. When it is, mass is less, energy is more. The energy release is in the form of gamma rays. What I want to do now is talk for a few minutes about the first experimental detection of electromagnetic radiation. So Maxwell comes up with the theory. Somebody has to verify that theory. And that task falls upon a guy named Heinrich Hertz. You've heard that name before. The unit for frequency is the Hertz. It's not a coincidence that the unit for frequency is Hertz, and Heinrich Hertz did experiments with electromagnetic radiation that has frequency associated with it. So here's what the experiment looked like. We call it a spark gap apparatus. What I'm going to circle in blue here is not critical to your understanding or even to you remembering. Okay, it's perspective. What I circle in red, that's important. That's what you got to take away from this. All right. So we start off with this spark gap apparatus. The spark gap apparatus consists of what we call an AC current. an AC power supply. AC stands for alternating current. What it really amounts to is oscillation of electric charge, electrons going back and forth, back and forth, back and forth. Now those electrons generate a magnetic field, a changing magnetic field. And that magnetic field in this piece of steel that you would have right here is changing and therefore generates an electric current over here on the secondary side. This electric current is different than the electric current in the primary coil. So is the potential difference. In fact, the potential difference increases. Why does it increase? Well, because we had 3 turns of wire over here, and we had, 6 or 7 turns of wire over there. It's called a step-up transformer. We're increasing the potential difference to a higher value. Why do we want to do that? Because we need a big potential difference over here. And why do we need a big potential difference over here on this side? Well, we have this little gap right here that we call a spark gap. Electrons with a small potential difference won't jump across that gap. Just like electrons that are up there in the clouds right now aren't going to jump from the cloud to the earth without a big potential difference. Big enough potential difference, the electrons jump, you get lightning. Big enough potential difference here, the electrons jump, you get mini lightning. So we use this step-up transformer, the details of which you don't really need to be that familiar with. We use this step-up transformer to get a big potential difference. That's important because that big potential difference causes the electrons to jump across this gap. Now, as the electrons were not moving on one side and then they jumped across, they accelerated. Hertz reasoned that if Maxwell's theory was correct, then these accelerating electrons would generate EMR. And then that EMR would be detected by the antenna, hence verifying Maxwell's theory. How is the antenna going to detect EMR? If we've never detected EMR before, how are we going to use an antenna to detect EMR? How do we know that an antenna would detect EMR? Well, if Maxwell's theory is correct, that EMR consists of a changing electric and a changing magnetic field, then there should be an electric current produced over here in the antenna. The changing electric field and the changing magnetic field will generate an electric current in the antenna. So here's the deal. Hertz flips on the switch. He reasons that if he detects an electric current in the antenna, then it must have been caused by a changing electric and changing magnetic field, which is exactly what Maxwell said EMR was. And if there is a changing electric and changing magnetic field, it must come from the accelerating charge, which is exactly where Maxwell said it was going to come from. So he reasons if he detects the current, then Maxwell's theory must be correct. He flips on the switch, guess what? He detects a current. So sure enough, he has, in his mind, verified Maxwell's theory by detecting EMR. The only thing that could have caused it was the accelerating charge. And the only thing that would have caused the current would have been the changing electric and magnetic fields that make up this EMR. Ethan? I don't know. I guess it's easier to say, the hard drive of your computer spins at 120 Hertz than it is to spin at 120 Maxwells, I guess. I don't know. Does that make a little bit of sense?
Well, maybe because
Now, the type of EMR that he detected was radio waves. He called them radio waves. We didn't distinguish between types of EMR before this, right? Because nobody ever detected it before. You detect EMR for the first time, you get to call it whatever you want. We now classify them in terms of radio waves, microwaves, infrared, and so on. But at the time, it wasn't like Hertz was trying to use radio waves. Oh, I'm going to choose to use radio waves in this experiment. There was no such thing as radio waves. They had never been observed before. He used what he used. And then when he verified that that's what it really was, he just named them radio waves. Why do you think he would have used radio waves? Let's take a break from writing for a second. Why do you think he would have used radio waves? It's easier to make them, right? It's easy to make radio waves. All you need is an oscillating electric charge. You don't need nuclear decay. Now, not that he would have known that gamma rays required nuclear decay at the time, right? He reasoned that this oscillating charge would produce this spark that jumped across the gap, accelerating charge, and it was easy to do. So he generated EMR. Hey, I got to name it something. Name it radio waves. We're talking about really, really low frequency radio waves, and then over time, then we classified other types of EMR as well based on frequency and wavelength and energy. All right, guys, I'm going to give you just a couple of minutes here to work on, probably about 5 or 6 minutes here, to work on some questions that you see on page 647. The questions of 647 would be questions 1 and 2, 5 and 7 to 14. You will not have enough time to work on those in class here today, but you will have a chance to get a start on them at least. You'll have to finish the rest of them up for homework tonight.